Hey guys, today we're going to be going over higher order functions. So, what are those? So, higher order functions, before we understand what those are, let's talk about the fact first that functions are data in Haskell. So, functions can be treated just like data of any other type. Basically, whatever you can do with a variable inside Haskell, you could also do with functions. So, this is known as having first class functions. We would say that functions are first class objects, and it allows some useful properties. So, one thing is that functions can be used as arguments for other functions. Okay. And functions can be defined using partial application. So, both of these first two properties basically allow you to create higher order functions. So, higher order functions, they're basically functions that take advantage of this first property. They're functions that take other functions as arguments. And even more interesting, when we have these functions that can take other functions as arguments, we can create these functions that then allow you to combine functions. Okay, so we can create these operators that allow the combining of other functions, just like with plus and minus and division, but for functions. So let's first examine what it means to have functions as arguments. So we've seen many functions that take other functions as arguments so far. So this includes map, folder, filter. We've seen plenty of these functions, and I'll point out all of these functions are higher order functions because they took another function as an argument. So another example is the zip width function. Let's take a look at this function. So zip width, it takes a function f as an argument. So you can see in its type signature how we bracket around the first three arguments. So we're saying the first argument f is actually a function in of itself that takes an a and a b and then returns a c. Okay? And then it takes two lists, a list of a and a list of b. What it does is it takes this f and the first elements of each of these two lists and it applies f to those first two elements and then continues building the list. So kind of it goes through the list. It's like zip instead of zipping each element together into a tuple, it zips it together with whatever function you give it f here. Okay. So functional programming, it's in the name, functional. In general, we make extensive use of functions and in particular higher order functions because higher order functions are functions making use of other functions in a very special way. And Haskell as language provides many mechanisms to work with these higher order functions. So consider some functions here like f here, okay? F is going to filter out all of the even elements from mapping the successor, so plus one, to a list of x's. Okay, so there's a number of ways that we could write this. We could write this like this, or we can get rid of these brackets with the dollar sign, which is a combinator that we'll go over in a bit. Or instead of explicitly, okay, specifying the argument in the function definition here, we can write it inside of a lambda expression here, or we could compose these two functions together using the dot here. This is another function combinator that we'll go over a bit, or we can use a lambda expression instead of using these predefined functions. Okay, so instead of writing even here, we could just put the even code into a lambda expression. And instead of writing successor here, we could do this just with plus one. Okay, so there's a lot of different ways we could write the same sort of functions in Haskell because Haskell gives us so many different mechanisms for manipulating how we write functions. And today we'll discuss a variety of these mechanisms and when you might want to use them. So let's discuss another property of functions in Haskell, which is partial application. So this actually has to do with currying, how we define functions, which we talked about before. So consider the following two array functions. So recall the arity of a function is just the number of arguments that takes. So a two array function just means that, well, it just takes two arguments to it. So add here takes an x and a y, and it just adds them together. So if we wanted to, we could define a unary function, okay, unary meaning one array is the same thing. So unary just means it takes one argument using partial application. So this is another consequence of having first class functions and having currying, that we can just say add one. Okay, we could partially apply it. We could give it one of its arguments, and add one returns a function. Okay, so if you give it just the one argument, it returns this function here, int n. Okay, and then we could write increment here is equal to this, and you'll notice increment here, it doesn't show an argument. There's no argument at here, but it does take an argument. It takes an int and then returns an int. So the argument is implicit because this add one, it returns a function, and then we're assigning increment to it like we would assign to a variable. So there's an implicit argument here. So if we look at the consequences of this, basically because of currying and partial application, technically any function with more than one argument, you can look at as returning another function. You can view it that way as it returns another function. You at least have the option of it having returning another function. A good example of a function you would regularly do this with would be the flip function. So flip, the way you define it, so flip, it would take a function as an argument. So an a and b goes to c. So this needs to be a binary function. And then it basically takes a b and an a and then goes back to c. So it's gonna flip these arguments around. Okay, so you could define it using a lambda expression. You could say take an x, y, and it's gonna take an f as an argument, and then it's gonna return a function, this lambda expression, that takes, we'll do it this way, a y and an x, and applies f x y. Okay, so it's going to take the arguments to this function in a different order here. Okay, if we look at how this might be used, we could take, let's say, div flipped, and we could flip around division. We could say flip and give it the division operator. And we actually need to call this, there already is a flip, this is a prelude function, so we'll call it flip prime. Okay, and if we look at how div flipped works, if we now open up a terminal, okay, so of course something like 1 div 2 is 0.5, but on the other hand, div flipped 1 2, okay, is 2.0, so it's doing the opposite there, right? So we could now give div, let's say we had a list of things and we wanted to divide everything in that list by 2. We could say something like map div flipped 2 to list of 4, 6, 8. Okay, and it's going to divide everything like 2 like this. And we could have even kind of skipped the 2 part. We could have said flip div and not even defined our own function fully here. And this would work the same way. If we do flip div and we kind of bracket this all to be like, okay, this is whatever this is returning. Okay, this returns a function, and then just use it like a function. So this is another example of how functions are first class in Haskell. Now, in talking about how functions can take functions as arguments and return functions, and how that's conveyed in the type signature, it's important to notice the syntax of that operator we use inside the type signature, that kind of arrow operator. So function application is left associative. That means when I call a function f of xy, okay, these brackets here are implicitly there. This is implicitly always happening. Okay, so this is not what's happening. This is what's happening. There's always this bracket here, and if there was more arguments, there'd be another bracket here that you would see. On the other hand, this arrow here is right associative. So this A goes to B goes to C is implicitly the same thing as A goes to bracket B goes to C. But not this. When you do this, okay, when you put the brackets on the left associativity side, that means that you're taking a function, A goes to B, as an argument here. Okay, so to relate this to our flip example, so flip here, if we look at its type signature, there's implicitly, so this type signature is the same thing as this, which is also the same thing as this. So that's what it means for this operator to be right associative, is that these brackets are just kind of implicitly there. Even if I don't put them there, that's how the precedence of this expression is being evaluated, right? And when I call f of x, or even if I have some function f x y z m equals, let's say the all add up together, right? Okay, this function, if I were to call it later, so if I were to create some variable, add some stuff, I would call f1 2 3 4. When I'm calling f1 2 3 4 here, this is actually the same as me writing f of 1, and then that returns a function, which then you call 2 on, which in turn returns another function, then you call 3 on, which in turn calls another function that you then call 4 on. And just a reminder, once again, I keep bringing this up, but this partial application really comes down to the feature of currying, okay, this idea that a function returns another function, and if we wanted to uncurry something, essentially what we do is we wrap it into a data type, the standard one being a tuple. So if we wanted to make sure that both of these arguments, like let's say x and y here, they're always given together before the function can be applied, you wrap it inside of a tuple. Now let's talk about an important feature that having these higher order functions gives us, which is function combinators. So we could take these functions that use other functions as arguments and use it as a way to combine functions in particularly interesting ways. So a very standard function combinator would be something called function composition, which might be something you recognize from mathematics. So we use the dot operator to express function composition. And basically what we do is we take a function that takes a b and returns a c, and another function that takes an a and returns a b, okay? And then we take an a and then return a c. So basically what it's doing is it's kind of chaining those functions together. So the simple way to define it is we take that a value, okay, and we apply it to our second function, g here. So g takes an a and returns a b, okay, so this returns a b value, and then our first function f here, that takes a b, so it's going to take the output of this function and then return a c, which is what we turn in the end here. So this way we could compose two functions together. So as an example of function composition, let's go back a second to that example we had before, where we had this even function and successor function, which should really be defined like this plus 1, okay? And what we were doing is we wrote this function, it goes over a list, it adds 1 to everything, and then it takes only the even values of that list using filter here, right? So another way we could have defined this, okay, is we could have said, well, this function, this filter even function, composed of map plus 1, okay? And then we don't even have to actually put our argument here. So this is one function composed of another function. So this returns another function f here. Okay, so it's the same. It's actually the same function. It gave me a different type signature here, but it is the same function. Let's go a. Okay, and then use that instead of. Okay. So this is actually a particular style of writing functions that's actually known as point free form. Before I go on to show you more combinators, let's point out another interesting, or perhaps the most boring function that Haskell has to offer, the identity function. So the identity, which we usually just write as it, is a function that takes an x and returns an x. It just returns the exact same thing. So this seems like the most useless function ever. In terms of actual practical computing, it kind of is. However, it's kind of neat to consider the properties that you could define using the identity function. So we wanted to define some properties that say map should hold. So you could define map like I showed you over other data types. And if you wanted to define a common property that map should hold, one of them should be that mapping the identity over the list x's will return that same list x's. So what does this mean? This means that whenever you define a map function, it shouldn't be like changing around the structure of the list or whatever data structure you're working off of arbitrarily. It shouldn't just be like changing things around. What it should be doing is it should be going and applying the function to each element of the list, right? So this gives you an idea of like, okay, this is some of the expected behavior out of map. This also gives us an idea about how the dot works, okay? So if we have a function f and we compose it with id, that should be the same thing as composing id with f. And in fact, having a function f composed of id should just be the same thing as if in general. So if you're interested in defining properties for how certain functions, particularly function combinators, should work, this identity function is actually pretty useful for that. And this is part of the reason why if you study functions from a more theoretical mathematics background, you'll talk about the identity function actually all the time. So let's talk about another example combinator here. So the $sign combinator is a very useful alternative to parentheses. So it's a bit of a weird definition. At first you're like, why would I ever define something like this? So it takes a function f and an argument x, and then just applies that function f to x. Now the trick is it's taking advantage of the associativity of function application that we just talked about before. So remember I just mentioned that function application is going to implicitly put brackets, okay, that associate to the left hand side there. So when you do this, okay, essentially you're getting brackets, you're bracketing stuff. So this allows us to take a function, like consider this first function Jimmy here, the first definition of it, where we're applying full $, to another thing, and we need to put brackets around this whole thing, and then we're applying again to another function, and we need to apply brackets to this whole thing, and then we need to apply brackets to this whole thing, and at the end we have this buildup of brackets, which can get kind of annoying. A lot of you probably are used to at the point now that whenever you do this, you wind up missing a bracket at the end here. A lot of you have had this experience most likely so far, where you miss a bracket and you're going around and you're counting brackets to make sure you have the right number. So we could use the $sign to overcome this. So instead of putting this first bracket here, we just put $sign here. And essentially what this is going to mean is that everything that comes after the $sign is going to become this x here. Okay? So we could bracket, instead of this bracket, we could put a $sign here. Instead of this bracket, we could put a $sign here. Now, we can't see these brackets here. We can't put a $sign here for this bracket. Why? Because if we did, it would mean that the bracket would continue until the end, right? Like it's the $sign is literally just saying whatever comes after this, the whole thing becomes bracketed, right? So we can't do that because we don't want everything after this opening bracket to be bracketed. We don't want this whole thing to be bracketed. We just want this part. So we couldn't put a $sign here, but the rest of these brackets we can, okay? And that'll stop this big buildup of brackets at the end there. Another alternative to the parentheses that we can make is, this isn't predefined, so we would have to define this ourselves in Haskell, although I kind of think that it should be predefined. We could rate it as this vertical bar arrow thing. I would call this a pipe, because it's doing essentially the same thing as the pipe operator in shell scripting does. If any of you have ever done some shell scripting before, you'll be very familiar with it. But for those that haven't, don't worry, I'll explain right now. So this pipe thing is kind of like the $, but in reverse. So the $, takes a function and then an X, okay? And it's kind of wrapping brackets around everything on the right of it, right? The pipe, on the other hand, is going to take the X and then the F. So it's kind of saying like bracket everything on the left-hand side and then feed it into the function on the right. So to look at an example of this, let's say we had a function that's going to print the map of 2 lower of the concatenation of interspersing this list with spaces. So it's like we take this list, we put spaces in between each thing, okay? And then we concatenate it, we put it all together into one thing, and then we map everything, we turn everything into lower cases, and then we print. So you'll notice right away that it's kind of easier to read things in reverse, right? So that's why this version here, in my opinion, is kind of better. So you start off with the list, and then you're saying intersperse it, and then you're saying concat that, okay, put it all together, and then turn everything into lowercase, and then print it. So it's kind of just two ways of looking at things. You can kind of move in like a top-down or bottom-up sort of way of evaluating this. Finally, before we finish off, it's worth mentioning that constructors for data types, okay, so when we have our data type, so we declare a data type, this is the data type name, and then each of the new values that we create on the right hand side that have other stuff attached to it, these are called constructors. That's one name for them. So these act like functions too. So if we have a constructor like student C that has 2 other values attached to it, okay, it kind of serves like a box that holds these 2 other values. This can be used just like a function, okay? So we could use it with our higher order functions. So let's say zip width here, we could use this to be like, well, if I have a list of strings and a list of int, and I want to take those lists and use the corresponding elements in each of those lists to make something of our student type, I could use zip width with the constructor student C, okay, to put those all together and then end up with a list of students like this. So this is just something interesting to be aware of. This is functional programming. A lot of things can be used as functions. The idea is functions are first class values. They can be used just like variables, and most things are functions or just values themselves. Okay, and with that, we'll leave off for today. We'll continue using higher order functions. We already kind of have been using higher order functions, particularly map and fold and stuff like that. Those are very important higher order functions. We'll continue using them as we go along. So there'll be plenty more higher order functions to come. Have a good one, guys.